Hi, this is Brett, and I'm here today to talk about image segmentation. And what I'd like to do is to give a high-level introduction to the topic of image segmentation. We're going to ask a couple of questions, in particular, what is image segmentation? Image segmentation at a high level is simply partitioning an image into different clusters or regions. Typically, this separates the foreground from the background. Often this is a binary separation, so they end up with a logical mask of an image. We might, for example, say that the foreground is logically true or 1, the background is logically false or 0. That's binarization. There might be more clustering than that you want to do. You might have multiple levels of clustering, but that's simply, very often it's simply a binarization. So next question is, why should we care? This is an easy question. I'll say that I've been doing image analysis for over 30 years. I've looked at a lot of different image processing problems and image analysis problems. Almost always there's some aspect of image segmentation. That is, I need to isolate the information that I'm interested in so that I can analyze it. I might be isolating based on color, based on intensity, based on shape. Whatever it is, it's still image segmentation. So let's give an example. This is an image called rice.ping that ships with MATLAB's image processing toolbox. And we want to ask the question, how many grains of rice are there in this image? Now, if I had one of these images to do, I might just simply come along and count them manually. But let's move on. Let's say that we have a lot of these images to analyze. We have a lot of images of rice, and we certainly don't want to do that manually. This is certainly an automatable problem. So one thing I'd like to do is to recognize first that this is a uint8 image. That means that the intensity values are integer valued, and they range from 0 to 255. And if I look at the different regions of that image, and I'm just going to look at the IMPixel tool, pixel region tool, as I drag this little reticle around the image, you can see that the intensity values get higher where the image is brighter, and lower where the image is darker. So it might suffice simply to set some kind of threshold. And let's say, for example, looking at this, that we set a threshold value and we say, I don't know, maybe at 150, set up a threshold of 150, anything above that threshold is true, anything below it is false. That might work. Another thing we might do is look at a histogram of the image, of the intensity values in the image. And here you can see again, there's this clustering of pixels that has an intensity value above 150. And let's just say that we manually want to select that value and show the image wherever that image is greater than 150, we want it to be true. Wherever it's less than 150, we want it to be false. And that is our first segmentation of this image. Now, we did a really nice job on top, but you can see that we've also under-segmented the bottom, so we didn't do a very good job on the bottom. That reflects the fact that the background intensity value is non-uniform. We can deal with that, and I'll show you how to deal with that in just a moment. But we don't typically want to manually have to select those thresholds. One thing we can do is to use a function called graythresh. Graythresh returns what we call the Atsu threshold value. So the Atsu, the graythresh is going to look at that histogram of intensities and automatically select that value for us. So if I do this, you'll see that Atsu threshold value is 131. And if we use that value, we get a better representation of the segmentation mask. Now, still some problems here. We still segmented the bottom, and we actually started to over-segment the top. We've got these regions that we don't want to count. So if we're just counting blobs, we're going to overcount up here and we're going to undercount down here. Now, first of all, let me point out a couple things. This process of setting this Atsu threshold and then creating this logical masking of the image is captured in a function called IMBinarize. So if I use just IMBinarize the image and return a BW matrix, I get the exact same value that I showed up here. Okay, so IMBinarize is very useful for this literal binarization thresholding. If we look at the documentation for IMBinarize, there's something else that I point out here. There's a few things you can do. There's some different parameters you can tweak. Here's the example that we're working with right now. But notice that there's this alternative syntax for using adaptive thresholding. And if I come along and just say I am binarize adaptive, we get a much, much better segmentation mask of that image. Okay, so our goal here was to count the number of grains. If I count blobs, I'm going to way overcount because I've got all these little noise in here. This video isn't about filtering or post-processing, but I'll just say really quickly, if we just did a search of our documentation, for example, for how do I remove small objects from a binary image, I find my way quickly to BW area open. You pass in a binary image. You say what's the smallest blob you want to, or the smallest blob you want to keep, and it passes out another binary image with those small blobs removed. So for example, we've got our binary image BW. I'm going to say let's get rid of anything that's 10 pixels or smaller, and now we have a really nice representation of our segmentation of our rice grains. And here I just used an IMI overlay to show that. If I just said IM show BW, we should see the binarization. These are just different visualization approaches. I can do a label overlay that allows you to set the transparency. Just different ways that you can visualize your results. So that's our segmentation mask. We asked the question, how many grains of rice are there? Lots and lots of ways to do that, to solve that problem as well. One of my favorite ways is just to count the number of connected components. So BW concomp, and you can find this in the doc really easily as well. BWCC equals BW concomp, and you'll notice that one of the outputs is number of objects. So we can quickly see that we've detected 96 grains of rice in that image. Okay, so that's pretty straightforward. One thing I like to point out though is that there are a lot of tools that make this even easier. And in fact, if you come to our apps toolbar and drop down, you'll see that there are a lot of different apps that extend the image processing and computer vision tools in MATLAB. Here, for example, is a color thresholder tool. We'll talk about that in a moment. There's an image segmenter tool. That sounds very useful for segmenting images. So let's come back and let's pass that image, the grayscale version of that image, into image segmenter. And here we'll see again, well, first MATLAB's going to ask us if we want to adjust the intensity range. You can say yes or no. It doesn't really matter for this case. But you'll see that there's lots of different approaches to solving this problem. Here, for example, is our threshold. There's the global threshold that we looked at initially. Here's a manual threshold, and I can specify the sensitivity. Here you can see I'm way over segmenting the top to get a good segmentation in the bottom. I'm perfectly segmenting the top, but I'm under segmenting the bottom. And then when I do my adaptive threshold, I'm getting a really nice result. I can show the binary, and very, very conveniently, once I have this, I can export not just the image, but a function that allows me to automate this process. So if I have 1,000 of these images to solve, I create a function called segment image, or whatever you want to call it, and I just, in a for loop, can pass over all those images and create those binary masks. Okay, so let's look at another example. That's a grayscale image, pretty straightforward to threshold it. What happens if we have color values, for example? So in this image, what if we ask the question, how many green chips are there? So that's a little bit more challenging. So we looked at the IM pixel region for rice.ping. Let's look at it for this one as well. And you can see that we've got a slightly more challenging problem, because while this is also uint 8, 0 to 255, we have 0 to 255 for red, green, and blue. And let's see if I drag this around. You can see that it's a little bit more challenging to select a threshold, because we really have to find 3 different thresholds that give us, that differentiate yellow from red and yellow from orange, and etc. So how do we do that? I already pointed out that there's a color thresholder app. So let's see what happens if we pass that image into the color thresholder app. It's actually a pretty easy problem. And you can see that you can look at this in multiple different color spaces: RGB, HSV, YCBR, CBCR, or LAB. You can probably solve this in any color space. Let's just select one. Let's just select. You can see that the red, green, yellow, orange, blue are all very nicely distinguished here in HSV space. So if I select this color space, I can just interactively start playing with different threshold sliders to set those HSV values separately. So look, there's my green, starting to get that. One thing I can do is just select my little lasso tool and say, I want green. So let's find all the green pixels, and I can just start tweaking from there, right? Or my favorite way to do this, if I reset the threshold, is in this point cloud representation of our image. Whoops. Cancel, sorry. Let's try it again. I can just select all the green pixels just like that. And very quickly I've isolated the green pixels. Just as I did before, I can show a binary representation. I can export not just the images, but a function. It's automatically going to capture those multiple thresholds for me. I can save this, for example, as create mask, or if I wanted to, create green mask. I've already saved this, so I'm not going to save that. But before I exit, let me just show you also that I can very quickly find yellow, right? I can find orange, I can find red, I can find blue, and I can just tweak this and just create different masks for each of those objects that I want. Each time I can put out a different function, and very quickly I can analyze my image. So here, for example, I've outputted or auto-generated create green mask, and there it is. I can show my image next to my segmentation mask of my green. Very, very convenient. And just like we did before with BW-ConComp, I can see that there are 6 green chips in that image. Nice. Okay, so we've looked at segmenting by grayscale threshold, grayscale intensity. We've looked at thresholding by color. What about, for example, shape? Well, let's take another look at coins.ping. And let's say, for example, that we wanted to segment everything that's a circle. So I have a lot of different circles here. I have a pen here that's certainly not a circle. Well, if I pass that image back into the image segmenter app, I'll just point out one more thing. I'm going to show you that there are a lot of different tools. You can try just auto clustering. That might give you what you need. But if you pull down here, let's reset that. Okay, let's set that to a new segmentation, and let's come down and say, new segmentation. Let's come down and say we want to, for example, find circles in the image. And when I find circles, this is implementing something called a Huff transform. There's a function in MATLAB called IamFindCircles. Pretty straightforward. You need to specify the minimum diameter and the maximum diameter of what you're looking for. So let's say a chip is about 48 pixels across. So let's say we have a minimum diameter of about 45 and a maximum diameter of about 55. Great. I say go, and nothing happens. Well, very interactively, I can change the sensitivity. I start finding some of those pixels, right, or some of those tokens. I can change it, make it more sensitive. Just kind of play with this a little bit. All right, so now I have a sensitivity. Well, all right, so I'm finding these. I'm just finding the yellow ones. Why is that? Well, there's this parameter called foreground polarity. It's bright by default, but if I set it to dark and I find it again, now I'm finding the other tokens or the other chips. So you can see how interactively I can play with this a little bit. Just as I did before, I can create my mask, and just as I did before, I can generate a function. You'll see that this is calling IamFindCircles behind the scenes. Circles to masks created my binary representation of those circles. So that just shows you another way of how you can segment your image. There's other things you might have seen in there. There's a segment SAM. SAM is a segment anything model. This is a deep learning approach to segmenting. If you have our 2006A or later, we introduced a tool that segments circles based on using a YOLO model. You only look once. So there's lots of different approaches. In fact, I think what I'd like to do is to finish up by just showing you or sharing with you the documentation for image segmentation here. So if I pull up to image segmentation, we have really nice documentation. You can see the apps that you can use for segmentation. We already talked about some of these. I am SegSam for the segment anything model. Lots of different approaches to segmenting, segmenting by grade connectivity, watershed, active contours, lazy snapping, grab cuts. So all kinds of things you can try out, and then different visualizations. Also, some really nice examples to get you started. Sometimes it's easier just to look at an example and find something similar to what you want to do, and just step in, and you can start modifying our code or just learning from our code. So that's about all I wanted to say about image segmentation. I'm going to say thank you. I hope that was useful, and see you next time.